Close your eyes and picture Earth from space. You've seen the photographs, the blue marble hanging in the blackness, swirling white clouds, vast blue oceans covering 70% of the surface, green and brown continents scattered across the globe. It's the most recognizable image in human history. Our home, beautiful, alive, welcoming. Now imagine looking at Earth from that same vantage point, but seeing something completely different. No blue, no green, no brown, just white. Pure, unbroken white stretching from the North Pole to the South Pole, from the Arctic to the Antarctic, across every ocean, over every continent, the entire planet encased in ice. Not ice at the poles with liquid oceans between. Not glaciers covering the high mountains with green valleys below. Ice everywhere. A frozen sphere reflecting sunlight like a mirror. A dead world. This wasn't a nightmare. This wasn't a failed planet in some distant solar system. This was Earth. Our Earth. 700 million years ago. For tens of millions of years, possibly longer, every ocean on the planet was frozen solid. Ice extended from the surface down hundreds of meters, perhaps a kilometer in places. The continents were buried beneath ice sheets that would make Antarctica's glaciers look modest. The tropics, where palm trees sway today, were locked in permafrost. The equator, where the sun beats down most intensely, was covered in glaciers that stretched to the horizon in every direction. Geologists call this period the Cryogenian. The name comes from Greek words meaning the birth of ice. And it's the most extreme climate event in Earth's history. A planetary catastrophe so severe that it should have ended complex life before it even began. A deep freeze that nearly turned Earth into a permanent ice ball orbiting a distant sun. But here's what should stop you in your tracks. Life existed during this freeze. Somehow, in conditions that seemed designed to extinguish all living things, organisms survived. They clung to existence in places you wouldn't think to look, in environments so marginal that they barely deserve to be called habitable. And when the ice finally melted, when Earth thawed after millions of years in a frozen tomb, those survivors didn't just recover, they exploded. They diversified into forms more complex than anything the planet had ever seen. The story of Snowball Earth isn't ancient history with no relevance to us. It's a story about how climate systems work, about how planets can tip from one extreme state to another, about feedback loops that amplify small changes into catastrophes, about life's resilience in the face of impossible odds, and about what happens when a world that seems stable suddenly isn't. Before we dive in, please consider subscribing and liking this video. Your support truly helps us continue this work. Thank you. Tonight, we're traveling back 700 million years to the coldest moment in Earth's history. We're going to watch a planet freeze solid. We're going to understand why the ice spread from pole to equator. We're going to find life hiding in places you'd never imagine. And we're going to watch Earth thaw, revealing a world transformed. This is Snowball Earth, and it's more terrifying, more beautiful, and more important than you ever imagined. Stand anywhere on Earth today and look at the sky. Clear or cloudy, day or night, what you're seeing is the result of a delicate balance. Energy from the sun reaches the planet. Some of that energy reflects back into space. Some gets absorbed by the ground, the oceans, the atmosphere. The absorbed energy warms the planet. The warm planet radiates heat back towards space. And somewhere in the middle of all this energy flowing in and out, Earth maintains temperatures that allow liquid water to exist. Liquid water. That's the key. Water freezes at 0 degrees Celsius and boils at 100 degrees. That's a narrow window, cosmically speaking. Venus, closer to the Sun, is too hot. Water boiled away billions of years ago. Mars, farther from the Sun and with a thin atmosphere, is too cold. Its water froze, and much of it was lost to space. Earth sits in what astronomers call the Goldilocks zone. Not too hot, not too cold. Just right. But just right isn't a permanent condition. It's a balance maintained by dozens of interacting systems. Change one thing, and other things change in response. Sometimes those responses stabilize the system, bringing it back toward equilibrium. But sometimes they destabilize it, pushing it further from balance. These are feedback loops, and they're what make climate both stable over long periods and dangerously unstable when pushed too far. The story of Snowball Earth begins with one of these feedback loops. It's called ice albedo feedback, and it's elegant in its simplicity and terrifying in its power. Albedo is a measure of reflectivity. How much sunlight does a surface bounce back into space versus absorb? Dark surfaces have low albedo. They absorb most of the light that hits them. Ocean water is dark. It absorbs about 94% of the sunlight that reaches it, converting that energy into heat. Forest canopies are relatively dark. Bare rock can be dark or light depending on composition. But ice is white, bright white. Fresh snow can reflect up to 90% of the sunlight that strikes it. Sea ice reflects 70 to 80%. Even old, dirty glacial ice reflects more than half the light that hits it. This difference matters. When sunlight hits ocean water, most of that energy stays in the climate system as heat. When sunlight hits ice, most of that energy bounces back into space, lost before it can warm anything. Now imagine what happens when a planet starts to cool. Perhaps the sun's output drops slightly. Perhaps volcanic eruptions inject particles into the atmosphere that block some sunlight. Perhaps continental drift moves land masses into positions that affect ocean currents. The specific trigger doesn't matter. What matters is that temperatures drop. When temperatures drop, ice forms. Ice caps at the poles grow larger. Mountain glaciers advance down valleys. Sea ice spreads from polar regions toward lower latitudes. And as ice spreads, more of the planet's surface becomes white. More sunlight gets reflected. Less energy gets absorbed. The planet cools further, which causes more ice to form, which reflects more sunlight, which causes more cooling, which causes more ice. The loop feeds on itself, growing stronger with each cycle. This is positive feedback, though there's nothing positive about it in the conventional sense. In science, positive feedback means a process that reinforces itself. More of something causes even more of it. It's the opposite of negative feedback, which dampens and stabilizes. Ice albedo feedback is positive feedback. And on Snowball Earth, it ran away completely. 720 million years ago, during the cryogenian period, Earth began to cool. We don't know exactly what triggered it. Perhaps it was a drop in atmospheric carbon dioxide caused by enhanced weathering of rocks. Perhaps it was changes in ocean circulation driven by the positions of continents. Perhaps it was a combination of factors that together tipped the climate in a colder direction. At first, the cooling was unremarkable. Ice caps grew, glaciers advanced. This had happened before in Earth's history. Ice ages came and went, driven by orbital variations and other factors. Life adapted. Ecosystems shifted toward the equator. Then, when the planet warmed again, they expanded back toward the poles. The cycle was natural and survivable. But this time, something different happened. The cooling didn't stop. The ice kept advancing. It spread from the poles down across the continents. It pushed into the oceans as sea ice formed on the surface. And once it reached a critical latitude, somewhere around 30 degrees north and south, the ice albedo feedback became overwhelming. Picture the ice spreading across a map of the globe. From the North Pole, it creeps down across Siberia, across northern North America, across northern Europe. From the South Pole, it advances across Antarctica and spreads toward what would become South America, Africa, and Australia. The ice is thick, miles thick in places, grinding across the landscape and scouring the bedrock beneath. In the oceans, sea ice forms on the surface wherever the water temperature drops below freezing. At first, this happens only at high latitudes, but as the ice spreads, it reflects more sunlight. The planet cools. The sea ice advances toward the equator, and here's where the catastrophe becomes inevitable. Once sea ice reaches about 30 degrees latitude, something like half the planet's surface is covered in white. At that point, so much sunlight is being reflected that the planet can't maintain its temperature. The cooling accelerates. Within perhaps a few thousand years, certainly less than 10,000, the ice races toward the equator. 30 degrees latitude, 20 degrees, 10 degrees, and then the unthinkable. Glaciers form at the equator. Sea ice covers tropical oceans. The entire planet from pole to pole is frozen. Snowball Earth has arrived. If you could have stood on the surface of Snowball Earth, anywhere on the surface, what would you have seen? The answer depends on where you were, but in every location, the landscape would have been dominated by ice. Near the poles, you'd have seen ice sheets like those covering Antarctica today, but even more extensive. Ice stretching to every horizon. The surface would have been relatively smooth, punctuated by pressure ridges where ice compressed and buckled. Crevasses would have split the surface, dark cracks descending into blue-white depths. In summer, if you could call it summer, the sun would circle the horizon without setting, but its light would have seemed weak and distant. In winter, darkness would have reigned for months. The temperature would have been extreme. At the poles, winter temperatures might have dropped to minus 80 degrees Celsius or colder. That's cold enough to freeze carbon dioxide out of the air. Dry ice would have formed as frost on the surface, creating eerie landscapes where both water ice and CO2 ice coexisted. Moving toward the equator, you'd have crossed continental ice sheets thousands of feet thick. These weren't static features. They flowed slowly but inexorably, driven by their own immense weight. Ice from the interior regions would have crept toward the coasts, eventually reaching the frozen oceans and either stopping at the shore or, in some places, flowing out onto the sea ice as ice shelves. The continents themselves would have been unrecognizable. Mountains, even tall mountains, would have been buried or reduced to rocky peaks poking through the ice. Valleys would have been filled. Rivers, of course, would have ceased to exist. No liquid water flowed anywhere on the surface. The hydrological cycle as we know it had stopped. But perhaps the most alien landscape would have been at the equator. Because here, where we expect warmth, where today rainforests thrive and coral reefs teem with life, you would have found glaciers, ice on the ground, sea ice on the oceans, permafrost extending deep into the crust. The sun would have been visible, rising and setting each day in a cycle that continued even in the frozen world. But the sun's warmth would have been insufficient to melt the ice. Even at the height of summer, even with the sun directly overhead at noon, temperatures would have remained well below freezing. Perhaps minus 30 degrees Celsius, perhaps minus 40. Cold enough that exposed skin would have frozen in minutes. Cold enough that breathing the air would have damaged lungs. The sky would have been clear, brutally, endlessly clear. Clouds require water vapor, and water vapor requires evaporation, and evaporation requires liquid water. But there was no liquid water on the surface. The air would have been dry, so dry that standing in it would have felt like breathing in a desert, except a desert so cold that moisture would freeze instantly. At night, the stars would have blazed with a clarity impossible to see on modern Earth. No city lights, no water vapor to blur the view, no clouds to block the sky. Just billions of stars arcing overhead, including stars visible only from the tropics. Stars we associate with warmth and life, now looking down on a frozen wasteland. The silence would have been profound. Wind, yes. The howling of air moving across ice would have been constant. And occasionally the deep groan of glaciers shifting, ice cracking under stress, the boom of crevasses opening. But no other sounds. No flowing water, no rain, no thunder, no living things making any noise at all. Just wind and ice and silence. This frozen world wasn't temporary. It wasn't a bad winter that gave way to spring. The ice persisted for millions of years, 10 million years perhaps. Some estimates suggest even longer. Entire geological epochs passed while Earth remained locked in freeze. During that time, nothing changed. Seasons came and went, but they were seasons of extreme cold and slightly less extreme cold. Summer at the equator was still colder than Antarctica in winter today. The landscape remained frozen. The ice remained. Year after year, century after century, millennium after millennium. Snowball Earth endured. And yet, life existed. Somewhere on this frozen planet, in conditions that seem utterly inhospitable, organisms survived. How? Where? These questions lead us to the evidence that Snowball Earth was real, and to the remarkable story of survival against impossible odds. The first time a geologist suggested that Earth had frozen completely, the idea was met with skepticism. The year was 1992. The geologist was Joseph Kirschvink, working at the California Institute of Technology. He coined the term Snowball Earth to describe what he believed had happened during the cryogenian period. His evidence was compelling but circumstantial. Glacial deposits in rocks from 700 million years ago. Not unusual by itself. Earth has had many ice ages, but these deposits appeared in rocks that had formed at tropical latitudes. Glacial debris at the equator. That was unusual. Other scientists had noticed this too, puzzled over it, proposed various explanations. Maybe the magnetic field had flipped, making north-south and south-north, so what seemed like tropical rocks were actually polar rocks. No, that didn't work. The rocks showed too many other indicators of tropical conditions. Maybe Earth's axis had tilted dramatically, putting the poles where the equator usually was. No, the physics didn't support that. Kirschvink's explanation was simpler and more radical. The glaciers had been at the equator because the entire planet had frozen. The simplicity was appealing. The implications were staggering. If Snowball Earth was real, it meant Earth's climate could tip into an extreme state and stay there for millions of years. It meant life had survived conditions far more severe than anyone had previously considered possible. It meant the history of our planet included an event more catastrophic than any asteroid impact or volcanic eruption. But proving it required more than glacial deposits at odd latitudes. It required multiple lines of evidence, all pointing to the same conclusion. The evidence came from rocks. Sedimentary rocks formed from material deposited at the bottom of ancient oceans. Geologists drilled cores, extracted samples, analyzed their composition and structure, and what they found built an overwhelming case. First, the glacial deposits themselves. These rocks, called diamictites, contain an unsorted mixture of sediment, ranging from fine clay to boulders the size of cars. This is the signature of glacial action. Glaciers don't sort material by size the way rivers do. They just grind everything up and deposit it in a jumbled mess when they melt. Diamictites from the Cryogenian period appear on every continent: Africa, South America, North America, Australia, Asia, even Antarctica. Everywhere geologists have looked for rocks of the right age, they've found glacial deposits. That suggests a global glaciation, not just regional ice ages. But more telling is where these deposits formed. By studying the magnetic orientation of minerals in the rocks, geologists can determine what latitude the rocks were at when they formed. Magnetic minerals align with Earth's magnetic field, and that field has a specific geometry. At the equator, magnetic field lines run parallel to the surface. At the poles, they point straight down. By measuring the angle of magnetization in ancient rocks, you can calculate the latitude where those rocks formed. The Cryogenian diamictites formed at low latitudes, some at latitudes between 5 and 15 degrees, essentially the tropics, glaciers in the tropics, ice at the equator. That's not a normal ice age. Second, cap carbonates. Directly above many of these glacial deposits, with no gap or intervening layers, sit thick deposits of limestone. This is strange. Limestone forms in warm, shallow tropical seas, where calcium carbonate precipitates out of the water. Why would limestone appear immediately after glacial deposits? The answer lies in what happened when Snowball Earth melted. For millions of years, volcanoes had continued erupting beneath the ice, pumping carbon dioxide into the atmosphere. With no weathering of rocks on ice-covered continents to remove it, the CO2 built up. Eventually, concentrations became so high that the greenhouse effect overpowered the ice albedo feedback. The planet warmed, the ice melted, and suddenly the oceans were exposed to an atmosphere containing perhaps 10% CO2 compared to 0.04% today. That CO2 dissolved into the ocean, reacting with minerals to form carbonic acid. The oceans became acidic. Then, as weathering resumed on newly exposed continents, minerals washed into the sea and reacted with the carbonic acid, precipitating out as calcium carbonate. Limestone. This process happened rapidly, geologically speaking, creating thick layers of cap carbonate that mark the end of the glaciation. The chemistry of these cap carbonates is bizarre. The ratio of carbon-13 to carbon-12 is extremely low, suggesting that the carbon cycle had been severely disrupted for a long period. This fits with a planet frozen for millions of years, where photosynthesis had nearly stopped and normal weathering had ceased. Third, banded iron formations. These are layers of iron-rich rock that form when dissolved iron in seawater encounters oxygen and precipitates out. They're common in rocks from Earth's early history, when the oceans contained lots of dissolved iron and photosynthetic organisms were just beginning to produce oxygen. But banded iron formations are rare in rocks younger than 1 billion years old, because by then the oceans had been oxygenated and the dissolved iron had already rusted and settled out. Except in cryogenian rocks, where banded iron formations appear again. Why? Because during Snowball Earth, photosynthesis in the ocean nearly stopped. Oxygen levels plummeted. Volcanoes continued to pump iron-rich fluids into the deep ocean. The iron stayed dissolved for millions of years. Then, when the ice melted and photosynthesis resumed, oxygen flooded back into the water. All that dissolved iron encountered oxygen at once and precipitated en masse, creating the iron formations. Fourth, drop stones. These are rocks, sometimes quite large, found embedded in fine-grained oceanic sediments. How did a boulder end up in the middle of mud that settled slowly to the ocean floor? The only explanation is that it was carried there by ice. Specifically, it was frozen into an iceberg, which drifted out to sea and then melted, dropping its rocky cargo to the bottom. Drop stones from the cryogenian appear in sediments that formed at tropical latitudes. Icebergs at the equator. Or rather, not icebergs in the sense of ice floating in liquid water, but chunks of ice breaking off from glaciers and moving across the frozen ocean until they melted from below, where geothermal heat from the ocean floor created thin pockets of liquid water. Every line of evidence points in the same direction. Global glaciation, ice from pole to pole, tropical oceans frozen solid. Snowball Earth was real. But this creates an almost insurmountable paradox. If Earth was frozen solid for millions of years, how did life survive? Life requires certain non-negotiable things: liquid water, energy, nutrients, a way to exchange gases and waste products with the environment. On Snowball Earth, all of these essentials seem to have vanished. The water was frozen. The energy from sunlight was reflected away by ice. Nutrients were locked in frozen ground and ice-covered oceans. Nothing could move. Nothing could flow. Nothing could grow. And yet, we know life survived. We know this because life existed before the freeze, and life existed after the melt, and the genetic continuity between them is unbroken. Complex eukaryotic cells, the kind with nuclei and organelles, existed before Snowball Earth. They existed afterward, more diverse than before. Something carried them through the freeze. The question isn't whether life survived. The question is where and how. The answer begins in the deepest parts of the ocean, in places where ice and cold couldn't reach, where Earth's internal heat created islands of habitability in a frozen world. Imagine descending through the ice covering the ocean. At the surface, temperatures are 50 degrees below zero. The ice is solid, rigid, stretching down tens of meters, perhaps hundreds in some places. But ice is a poor conductor of heat. As you descend through it, the temperature gradually rises. Not from the sun above, which has no power to penetrate so far, but from below, from the ocean beneath the ice. Eventually, you reach the bottom of the ice sheet. Here, the temperature has climbed to the freezing point of seawater, about -2 degrees Celsius. Below you is darkness. Liquid water. Not much of it, and not everywhere, but it exists. Pockets of liquid water trapped between layers of ice. Thin layers of brine too salty to freeze. And in some places, especially near the equator where the sun's rays could penetrate thin ice, perhaps larger bodies of liquid water persisting beneath a frozen lid. This water is cold, dark, nearly sterile, but it's liquid. And where there's liquid water, there's a chance for life. The water wouldn't have been still. Ocean currents, driven by differences in temperature and salinity, would have continued to circulate, albeit slowly. These currents would have carried nutrients from the continents, minerals dissolved from rocks, and most importantly, they would have connected different parts of the ocean, preventing complete stagnation. In this dark, cold water, simple organisms could have persisted. Bacteria, archaea, single-celled eukaryotes. These organisms didn't need sunlight. Many modern microbes don't. They derive energy from chemical reactions, feeding on hydrogen sulfide, methane, iron, manganese, or other compounds dissolved in the water. Where would these compounds have come from? From the ocean floor, from hydrothermal vents. Hydrothermal vents are underwater hot springs, where seawater seeps into cracks in the ocean floor, gets heated by magma below, and then erupts back into the ocean carrying dissolved minerals and gases. Today, entire ecosystems thrive around these vents. Tube worms, clams, crabs, fish, all ultimately dependent on chemosynthetic bacteria that feed on the chemicals pouring from the vents. During Snowball Earth, these vents continued to operate. The ice above made no difference to the processes happening kilometers below. Magma still rose toward the surface. Water still circulated through hot rocks. Chemicals still dissolved and erupted into the ocean. At these vents, in the darkness beneath the ice, life could have survived. Not thrived, not diversified into new forms, but survived. Bacteria clustered around vent openings, metabolizing sulfur compounds. Other microbes fed on the bacteria. Simple eukaryotes might have grazed on the bacterial mats. It was a minimal ecosystem, stripped down to the bare essentials. But it was life. The number of these refugees would have been limited. Hydrothermal vents are scattered across the ocean floor, separated by vast stretches of inactive seafloor. The organisms living at each vent would have been isolated from those at other vents. Populations would have been small. Genetic diversity would have declined as generation after generation passed in isolation. But they didn't go extinct. Enough vents existed, scattered across enough of the ocean floor, that populations persisted. When the ice finally melted millions of years later, the descendants of these survivors emerged to recolonize the oceans. Hydrothermal vents couldn't have been the only refugees. They're too scattered, too specialized. Other organisms, particularly photosynthetic ones, needed different solutions. Consider the ice itself. Not all ice is created equal. Near the poles, where temperatures were coldest, the ice would have been thick, opaque, and completely dark below. Nothing could photosynthesize under such ice. But near the equator, conditions were different. Even during Snowball Earth, the equator received more sunlight than higher latitudes. The sun's rays struck more directly. And while most of this light was reflected by the white ice surface, not all of it was. Some penetrated the ice, especially if the ice was relatively thin, or if it had been partially melted and refrozen, creating clear zones. Experiments with modern sea ice show that sunlight can penetrate surprisingly far through thin or clear ice. Under the right conditions, 1% or more of surface sunlight can reach the bottom of ice several meters thick. 1% doesn't sound like much, Its dim light, barely enough to see by. But for photosynthetic organisms adapted to low-light conditions, it's enough. Photosynthetic bacteria could have survived in the water directly beneath thin ice near the equator. They would have grown slowly, starved for light, but not completely deprived of it. They would have reproduced rarely. Their populations would have been tiny compared to the vast blooms that occur in sunlit oceans. But they would have survived. These bacteria were critical. They produced oxygen, though in minute amounts. They converted carbon dioxide into organic matter, creating the base of a food chain. Other organisms could eat them. The oxygen they produced could support simple animals or eukaryotes that needed it for respiration. It was a tenuous existence. During the depths of winter, even near the equator, darkness would have been total. The bacteria would have gone dormant, waiting for the return of light. During summer, when the sun's path across the sky brought more direct illumination, they would have grown. This seasonal cycle would have repeated for millions of years, each generation maintaining the species until conditions improved. There's another possibility, one that sounds almost absurd until you consider the evidence from modern analogues. Life might have survived on the surface of the ice. In Antarctica today, in the dry valleys and on the polar plateau, where conditions are about as harsh as anywhere on Earth, scientists have found liquid water on top of the ice during summer. Not much. Small pools in depressions, perhaps a few centimeters deep, formed when sunlight melts a thin layer of surface ice. These pools freeze again within hours or days, but while they exist, they're habitable, and they are inhabited. Cyanobacteria form mats at the bottom of these temporary pools. When the water freezes, the bacteria go dormant. When it melts again, they resume activity. They photosynthesize, reproduce, and grow during brief windows of opportunity, then shut down and wait when conditions turn harsh again. During Snowball Earth, similar pools might have formed near the equator during summer. The ice surface there would have been cold, perhaps -20 or -30 degrees Celsius on average. But during peak summer, with the sun high in the sky and reflecting off the white ice, localized warming could have created temperatures just above freezing in protected depressions. Water from melted ice would have pooled. For a few hours or days, liquid water would have existed on the surface. Photosynthetic bacteria that happened to be present could have grown. When the pool froze again, they would have gone dormant, freeze-tolerant structures waiting for the next thaw. This seems like an impossibly precarious way to survive. And it was. But evolution doesn't optimize for comfort. It optimizes for survival. If a lineage can survive by growing for a few hours per year and being dormant the rest of the time, that's enough to avoid extinction. The survival of life during Snowball Earth wasn't about thriving. It was about not dying. About maintaining presence in whatever marginal refugees existed, no matter how small or temporary. And when conditions finally changed, when the ice melted and the oceans opened up again, those surviving lineages exploded outward from their refugees to fill a world emptied by catastrophe. But why did conditions change? If the ice albedo feedback was strong enough to freeze the planet, why didn't it keep the planet frozen forever? What melted Snowball Earth? The answer lies not in the ice or the oceans or the atmosphere. It lies deep beneath the surface, in the hot mantle that drives plate tectonics and volcanic activity. Volcanoes don't care what's happening at the surface. The heat that powers them comes from hundreds of kilometers down, from radioactive decay and residual heat from Earth's formation. That heat drives convection in the mantle. Molten rock rises toward the surface. Plates move. Magma breaks through weak points in the crust. During Snowball Earth, this process continued uninterrupted. In fact, because the surface was frozen and therefore more rigid, some geologists believe volcanic activity might have actually increased. With no flowing water to lubricate faults and no weathering to erode volcanic edifices, pressure could have built up more easily, leading to more frequent or more violent eruptions. Every volcanic eruption releases gases into the atmosphere: water vapor, sulfur dioxide, and most importantly for our story, carbon dioxide. CO2 is a byproduct of magma formation. When rocks melt deep in the mantle, dissolved gases come out of solution. When that magma erupts at the surface, those gases are released into the air. On normal Earth, the carbon cycle maintains atmospheric CO2 at levels that keep the planet habitable. Volcanoes release CO2. Chemical weathering of rocks removes it. Rain falling on continental rocks slowly dissolves them, creating solutions that wash into the ocean. In the ocean, the dissolved minerals react with CO2 to form calcium carbonate, which precipitates out and eventually becomes limestone. This process locks carbon away in rocks, removing it from the atmosphere. The system stays in balance because the rate of CO2 removal depends on temperature and rainfall. When the planet is warm, more rain falls, weathering accelerates, and CO2 is removed faster. The planet cools. When the planet is cool, less rain falls, weathering slows, and volcanic CO2 builds up. The planet warms. It's a negative feedback loop, a thermostat that keeps Earth's temperature within a habitable range. But on Snowball Earth, the removal side of the cycle stopped. The continents were covered in ice. No rain fell. No water flowed over rocks. Weathering ceased almost entirely. Similarly, in the frozen oceans, the organisms that normally consume CO2 through photosynthesis were reduced to tiny populations in scattered refuges. They weren't removing carbon in any significant amount. But volcanoes kept erupting, and CO2 kept accumulating in the atmosphere. At first, this made no difference. The planet was so cold, and so much sunlight was being reflected by the ice that even rising CO2 levels couldn't warm things up. The greenhouse effect was overwhelmed. You can trap heat all you want, but if no heat is being absorbed in the first place because all the sunlight is reflected away, there's nothing to trap. So the CO2 rose. From pre-freeze levels of perhaps a few hundred parts per million, concentrations climbed into the thousands, then tens of thousands, eventually hundreds of thousands of parts per million, perhaps even higher. For perspective, today's atmosphere contains about 420 parts per million CO2. During Snowball Earth, by the time the melt began, atmospheric CO2 might have been 1,000 times higher, 10% of the atmosphere or more. At those concentrations, CO2 isn't just a trace gas. It's a major component of the air. And at those concentrations, the greenhouse effect becomes powerful enough to overcome even the albedo of a frozen planet. The atmosphere becomes so good at trapping heat that even the small amount of sunlight absorbed by ice-covered Earth is enough to start raising temperatures. The warming began slowly. Average global temperature might have risen from minus 50 degrees to minus 40, then minus 30. Ice that had been stable for millions of years began to show signs of stress. At the equator, where the sun's radiation was strongest, the ice started to thin. Surface melting occurred during summer, creating puddles and pools that refroze at night, but appeared again the next day. And then, at some critical threshold, the feedback loop reversed. Melting ice exposed dark water. Dark water absorbed more sunlight than ice. Temperature rose further. More ice melted. The positive feedback that had frozen the planet now worked in reverse to thaw it. The transition might have been rapid, geologically speaking. What took millions of years to freeze might have melted in just thousands of years, perhaps even faster. Computer models suggest that once the melt began, it could have accelerated dramatically, with ice retreating from the equator toward the poles in less than a millennium. Imagine standing at the equator during this time. The ice, which had been solid and unchanging for longer than memory, longer than species, suddenly begins to crack. Dark leads of open water appear. They widen. The sound of breaking ice echoes across the landscape. Icebergs carve from the edges of the sea ice and drift in newly opened water. The temperature is rising, not gradually, quickly, within a human lifetime. If humans had been there to witness it, the climate would have swung from the depths of freeze to something approaching normal. Within a few lifetimes, it would have swung past normal into a greenhouse state, hotter than Earth had experienced in hundreds of millions of years. Because here's the cruel irony. The same CO2 that saved Earth from permanent freeze also pushed it into an extreme greenhouse. All that carbon dioxide, accumulated over millions of years of volcanic outgassing, was still in the atmosphere. It had been necessary to melt the ice, but now the ice was melting and the CO2 remained. And with the ice gone, with dark oceans absorbing sunlight instead of white ice reflecting it, the greenhouse effect became overpowering. Temperatures soared. The planet that had been 50 degrees below zero at the equator might have swung to 50 degrees above zero. From frozen wasteland to sweltering hothouse in a few thousand years. The climate whiplash would have been extreme beyond anything in modern experience. The newly exposed oceans absorbed some of the atmospheric CO2. As the gas dissolved in seawater, it formed carbonic acid. The oceans became acidic, with pH levels dropping significantly. This would have been hostile to many forms of life trying to recolonize the seas. Organisms with calcium carbonate shells would have struggled. The acid dissolved their protective structures, but the weathering of rocks, resumed on newly ice-free continents, began to remove CO2 from the atmosphere and deliver minerals to the ocean. These minerals reacted with the carbonic acid, neutralizing it and precipitating out as calcium carbonate. This is what created the cap carbonates, those thick limestone layers that sit directly on top of the glacial deposits in the rock record. The process took time, tens of thousands of years, perhaps hundreds of thousands. But eventually, atmospheric CO2 declined to more normal levels. The extreme greenhouse began to moderate. The climate stabilized into something more habitable, and life, emerging from its refuges, began to reclaim the planet. The organisms that survived Snowball Earth were the lucky ones, or perhaps the specially adapted ones. Either way, they found themselves in a world that was emptied of competition, rich in nutrients, and ready to be colonized. The oceans, starved of nutrients for millions of years while locked under ice, suddenly received an influx of minerals from weathering continents. glaciers had scoured the land, grinding rocks into fine sediment. When the ice melted, this sediment washed into the sea, carrying phosphorus, iron, nitrogen, and other essential elements. Photosynthetic bacteria, freed from the constraint of dim light beneath ice, exploded in abundance. Vast blooms covered the surface of the ocean. These blooms produced oxygen, lots of it. For the first time in Earth's history, oxygen levels in the atmosphere and oceans might have risen to something approaching modern levels. Higher oxygen levels made new forms of life possible. Complex, multicellular organisms require more oxygen than single cells. Building and maintaining a large body, coordinating multiple cell types, moving through the environment, all of this demands energy. And the most efficient way to generate biological energy is through oxygen-based respiration. Before Snowball Earth, oxygen levels were low, perhaps only a few % of current levels. This might have been one of the factors limiting the evolution of complex life. But after the thaw, with photosynthesis ramping up and oxygen production accelerating, that constraint was lifted. Within a few tens of millions of years after the end of the Cryogenian, the first large multicellular organisms appear in the fossil record. These are the Ediacaran biota, named after the Ediacara Hills in Australia, where many of the fossils were discovered. The Ediacaran organisms were strange. They didn't look like anything alive today. Some resembled fronds, anchored to the seafloor and swaying in currents. Others looked like quilted mattresses or fractal branches, or circular discs covered in radiating ridges. They ranged in size from a few centimeters to over a meter across. Paleontologists still debate what these organisms were. Some might have been early animals. Others might have been fungi or algae, or something entirely extinct, a failed experiment in body plans that didn't survive into later periods. But whatever they were, they represented a revolution. Life was no longer confined to microscopic single cells. It was building bodies, experimenting with size and structure. And then, about 540 million years ago, came the Cambrian explosion. In a period of perhaps 15 to 20 million years, every major group of animals alive today appeared in the fossil record. Arthropods with jointed legs and external skeletons, mollusks with shells, worms that burrowed through sediment, creatures with eyes and teeth and predatory behaviors. The diversity was staggering. The speed was unprecedented. Evolution, which had produced mostly single-celled organisms for 3 billion years, suddenly generated complex animals with sophisticated body plans and behaviors in less than 1% of that time. Why? What changed? The answer almost certainly involves multiple factors. Higher oxygen levels, as we've discussed, an influx of nutrients into post-glacial oceans, the extinction of many older lineages during Snowball Earth, clearing ecological space for new innovations. But there's another factor worth considering. Snowball Earth might have selected for genetic and developmental flexibility. Organisms that survived the freeze were those that could tolerate extreme conditions, that could shut down and wait, that could adapt quickly when conditions changed. These traits, evolved under the pressure of the freeze, might have been exactly the traits needed for rapid diversification afterward. It's also possible that the extreme isolation during Snowball Earth, with populations scattered in tiny refuges, accelerated genetic divergence. Small, isolated populations evolve faster than large, interconnected ones. Mutations that might have been diluted in a large population can become fixed in a small one. By the time the ice melted, populations that had been the same species before the freeze might have diverged into separate species. When they came back into contact in the post-glacial oceans, they didn't merge back together. They remained distinct and continued to diverge. The Cambrian explosion might not have been a single explosion at all, but rather the culmination of millions of years of evolution that happened in isolation during Snowball Earth, only becoming visible in the fossil record when ice melted and conditions allowed fossilization. Whatever the exact mechanism, the connection between Snowball Earth and the explosion of complex life seems clear. The catastrophe and the flowering, the near extinction and the diversification. One led to the other in ways we're still working to understand fully. But the lesson is profound. Catastrophes don't just destroy, they also create opportunities. They reset the rules. They clear away the old and make room for the new. Life before Snowball Earth was ancient, established, occupying every available niche. After Snowball Earth, the world was younger, emptier, full of possibility. The survivors didn't just refill the old niches. They invented new ones. They built bodies that could move and sense and hunt. They developed hard parts like shells and skeletons that could preserve as fossils, finally giving us a clear window into what life looked like. They created ecosystems with predators and prey, with competition and cooperation, with complexity far beyond anything that came before. In a very real sense, the modern biological world traces its origin to the aftermath of Snowball Earth. The animals that crawled and swam and burrowed in the Cambrian seas were the ancestors of everything that followed. Fish, amphibians, reptiles, mammals, birds, all of them descended from the survivors of Snowball Earth, which means we did too. Every vertebrate alive today, including humans, can trace its lineage back through the Cambrian to the Ediacaran, and ultimately to those organisms that endured the freeze in hydrothermal vents, beneath thin ice or in temporary meltwater pools. We exist because they survived. Our complexity is built on the foundation they laid after the ice melted. Snowball Earth happened 700 million years ago. That's so far back, it feels almost mythological. Humans have existed for perhaps 300,000 years. Civilization emerged about 12,000 years ago. Industrial society is barely 300 years old. Against the vast span of geological time, we're newcomers, brief visitors to a planet with an ancient and turbulent history. But the lessons of Snowball Earth aren't ancient history. They're warnings written in stone about how climate systems work, about feedback loops that can spiral out of control, about tipping points that, once crossed, can lock a planet into extreme states for millions of years. The ice albedo feedback that froze Earth still operates today. We see it in action in the Arctic, where sea ice has been declining for decades. As ice retreats, dark ocean water is exposed. That dark water absorbs more sunlight than the white ice it replaced. The Arctic warms faster than the rest of the planet. More ice melts. More dark water appears. The warming accelerates. This is the same feedback loop that created Snowball Earth, just operating at a smaller scale and in a different direction. Instead of runaway cooling, we're experiencing enhanced warming in polar regions. The physics is identical, only the circumstances differ. We're not headed for another Snowball Earth. The conditions that created it were unique. Continental positions that allowed ice sheets to grow at mid-latitudes. a sun that was somewhat dimmer than today, an atmosphere with less greenhouse gases to start with. But the principle remains. Climate systems have feedback loops, and those loops can amplify small changes into large ones. Today, we're conducting an experiment with Earth's climate. We're adding carbon dioxide to the atmosphere at a rate unprecedented in geological history, certainly unprecedented over timescales relevant to human civilization. We've raised CO2 from pre-industrial levels of about 280 parts per million to over 420 today. That's a 50% increase in less than 2 centuries. This doesn't sound like much compared to the hundreds of thousands of parts per million that accumulated during Snowball Earth. But context matters. That CO2 built up over millions of years and was necessary to melt a frozen planet. Our CO2 is being added in decades and is warming an already habitable world. The question isn't whether Earth will survive. Earth survived Snowball Earth. It will survive whatever we do. The question is whether we're pushing the climate system toward a tipping point that will make the planet significantly less hospitable for human civilization. Climate scientists have identified several potential tipping points in the modern climate system. The collapse of major ice sheets, which would raise sea levels by meters. The shutdown of ocean circulation patterns like the Atlantic meridional overturning circulation, which would dramatically alter climate in Europe and North America. The release of methane from thawing permafrost, which would accelerate warming. The dieback of rainforests, which would reduce the planet's capacity to absorb CO2. Any one of these could push the system into a new state that persists far longer than the perturbation that caused it. Not millions of years like Snowball Earth, but potentially thousands of years. Long enough that dozens of human generations would have to deal with the consequences of decisions made by ours. Snowball Earth teaches us that climate stability is not guaranteed. That the pleasant, habitable conditions we've enjoyed for the past 10,000 years aren't the default state of the planet, but rather one configuration among many possible ones. That the systems maintaining that habitability have limits, and pushing them too hard can trigger changes we can't easily reverse. But Snowball Earth also offers an unexpected form of hope if we look far beyond our own planet and ask, where else might life exist in the universe? For decades, astronomers have searched for planets in the habitable zone, that narrow band around a star where temperatures allow liquid water on the surface. It's a reasonable place to start. Life as we know it requires liquid water. But Snowball Earth shows that habitability isn't that simple. A planet could be in the habitable zone and still freeze solid. Or it could tip into a runaway greenhouse like Venus. Being the right distance from the right kind of star isn't enough. You also need the right atmosphere, the right amount of greenhouse gases, the right continental configuration, the right feedback mechanisms. But here's where Snowball Earth becomes encouraging rather than discouraging. Life survived a global freeze. It survived in refuges we wouldn't have predicted. Hydrothermal vents beneath kilometers of ice, thin layers of water under translucent ice, temporary meltwater pools on the surface. If life can survive those conditions on Earth, might it survive similar conditions elsewhere? Consider Europa, Jupiter's ice-covered moon. Its surface is frozen solid, has been for billions of years. Surface temperatures hover around minus 160 degrees Celsius. No sunlight reaches the surface with enough energy to drive photosynthesis. By most definitions, Europa is inhospitable to life. But beneath that ice, perhaps 10 to 15 kilometers down, there's an ocean, a global ocean of liquid water kept from freezing by tidal heating. As Europa orbits Jupiter, the giant planet's gravity flexes the moon, generating heat through friction. That heat keeps the subsurface ocean liquid. And at the bottom of that ocean, there are almost certainly hydrothermal vents. Places where Europa's rocky core meets the ocean, where heat escapes and minerals dissolve. Exactly the kind of environment where life survived on Snowball Earth. We haven't found life on Europa. We don't even know if it exists. But Snowball Earth tells us it's possible, that life doesn't need sunlight if it has chemical energy, that an ice-covered ocean isn't necessarily dead, that the refugees we discovered on frozen Earth might have analogues on frozen moons. Saturn's moon Enceladus offers similar possibilities. It's smaller than Europa, but it too has a subsurface ocean. We know this because Enceladus shoots geysers of water into space from cracks in its south polar ice. The Cassini spacecraft flew through these geysers and analyzed their composition. The water contains organic molecules, salts, and evidence of hydrothermal activity. If life exists on Enceladus, it's living in conditions remarkably similar to the hydrothermal refuges of Snowball Earth. No sunlight, freezing temperatures at the surface, but liquid water, chemical energy, and minerals from geological activity below. The discovery that Earth once froze completely and that life survived has expanded our conception of habitability. We now search for life in places we might previously have dismissed as too cold, too dark, too isolated. If life clung to existence beneath Earth's ice for millions of years, it might be doing the same thing right now beneath the ice of Europa or Enceladus, or any number of other frozen worlds in our solar system and beyond. This is one of the most profound legacies of Snowball Earth research. It changed our understanding not just of Earth's history, but of life's requirements and possibilities. It taught us that life, once established, is remarkably difficult to extinguish completely, that it finds ways to persist in marginal environments, that catastrophes that would seem to preclude life's survival might only reduce it to scattered refuges from which it later expands. There's also a more philosophical dimension to Snowball Earth. It forces us to confront the role of catastrophe in the history of life and in the universe more broadly. We tend to think of progress as gradual, species slowly adapting to their environments, technology incrementally improving, civilizations building on the achievements of those that came before. And much of the time, that's true. Change accumulates slowly through countless small steps. But the history of Earth is also punctuated by catastrophes, asteroid impacts, volcanic eruptions, ice ages. Each one causes massive disruptions. Each one seems in the moment like an ending. Species go extinct. Ecosystems collapse. The world becomes harsher, more dangerous, less hospitable. And yet, from a longer perspective, these catastrophes also create opportunities. They clear away established patterns. They remove dominant species and allow previously marginal ones to expand. They reset the rules and allow evolution to explore new possibilities. Snowball Earth was perhaps the most extreme of these catastrophes. It reduced life to its simplest forms, scattered across the most marginal habitats. It came closer than any other event we know of to extinguishing complex life entirely. But in surviving it, life proved its resilience. And in the aftermath, life reached heights of complexity it had never achieved before. The Cambrian explosion, with its profusion of new body plans and behaviors, came after Snowball Earth. Perhaps because of Snowball Earth. Does this mean catastrophes are good? Not in any moral sense. The organisms that die during a mass extinction don't benefit from what comes after. Suffering is real. Loss is real. But in the long arc of history, catastrophes do seem to play a creative role. They break up stable patterns that might otherwise persist indefinitely. They create space for innovation. This isn't a comfortable lesson. It doesn't help the species going extinct during a mass extinction to know that something interesting might evolve afterward. But it does provide perspective on our current moment. We're facing potential catastrophes: climate change, biodiversity loss, environmental degradation. These are serious threats that demand serious responses. But they're not existential threats to life itself. Life has survived far worse. It survived Snowball Earth. It will survive us. The question is whether we'll survive ourselves. Whether human civilization can navigate the challenges we've created without collapsing into chaos. Whether we can manage the power we've gained over planetary systems without triggering changes that make Earth significantly less habitable for our species. Snowball Earth offers both warning and hope. Warning because it shows how easily a stable climate can tip into an extreme state. How feedback loops can amplify small changes into catastrophic ones. How long it can take to recover from extreme conditions. Hope because it shows that recovery is possible. That even the most extreme catastrophes eventually end. That life endures and adapts and ultimately thrives. That the systems driving Earth's climate, while powerful, are not infinite. They have limits and eventually restore balance. The timescales are the problem. Snowball Earth took millions of years to develop and millions of years to end. Human civilization operates on timescales of decades and centuries, not millions of years. We can't wait for geological processes to fix what we've disrupted. We have to understand the systems and actively manage our impact. And so we return to where we began, to that image of Earth from space, the blue marble that has become the symbol of our planet and our species. That image, taken by Apollo astronauts in 1972, shows a world of stunning beauty. Blue oceans, white clouds, green and brown continents, a planet alive and welcoming. But now, having traveled back 700 million years, having watched that same planet freeze solid and remain frozen for millions of years, having followed life as it survived in scattered refugees and then exploded into complexity when the ice melted, we see that image differently. We see a planet in balance, yes, but also a planet capable of extreme states, a planet that has been a frozen ice ball and a steaming hothouse, a planet that has nearly lost all complex life and then regenerated more diversity than before, a planet that is dynamic, changing, never truly stable for long. The blue marble we see from space is one configuration, one moment in a long history of change. The conditions that make it blue and green and habitable aren't permanent. They're maintained by complex, interconnected systems that we're only beginning to understand fully. Snowball Earth froze 700 million years ago. The ice melted. Life survived and thrived. Today, we stand on continents that were once buried beneath miles of ice. We breathe air whose composition was influenced by the photosynthetic organisms that survived the freeze. We exist because those organisms endured the impossible and passed life forward to the next generation and the next and the next across hundreds of millions of years until here we are. That continuity is profound. Every living thing on Earth today carries in its DNA the legacy of survival from Snowball Earth. We are all descendants of the lucky, the hardy, the adaptable few that found refuges in a frozen world and waited for the thaw. The rocks remember that frozen time, the glacial deposits, the cap carbonates, the iron formations. They tell a story of catastrophe and recovery, of extinction and innovation, of a planet pushed to its limits and life refusing to surrender. What story will future geologists read in the rocks we're creating now? Will they see evidence of a species that recognized the power it had gained over planetary systems and used that power wisely? Or will they see the markers of a brief crisis, a rapid change in atmospheric composition, a wave of extinctions, followed by recovery, but in a world significantly altered? The answer depends on what we do next, on whether we learn the lessons written in ancient rocks, on whether we understand that climate can tip, that feedbacks can amplify, that changes can persist far longer than we'd wish. Snowball Earth was real. It happened. The planet froze, stayed frozen for millions of years, and eventually thawed. Life endured in refuges we're still discovering and understanding. And when the ice melted, life exploded into forms and complexity that set the stage for everything that followed, including us. That frozen world is our past. It shaped our planet and ultimately made us possible. The question now is whether we'll let that past inform our future, whether we'll recognize that the stability we take for granted is precious and fragile, whether we'll act with the wisdom that should come from understanding deep time and planetary history. The ice albedo feedback that froze Earth 700 million years ago still operates. The climate tipping points that once locked the planet in an extreme state for millions of years still exist. The difference is that now, for the first time in Earth's history, there's a species aware of these processes, a species capable of understanding them, and potentially a species capable of managing its impact to avoid triggering them. Snowball Earth teaches us what's possible when climate tips, but it also teaches us that catastrophes end, that life is resilient beyond what we imagine, that even the most extreme conditions eventually give way to recovery and renewal. 700 million years is almost impossible to comprehend. It's a span of time that dwarfs human experience, that predates not just our species, but our entire lineage back dozens of evolutionary branchings. Yet the rocks from that time are still here, still telling their story, still teaching us about our planet's capacity for both catastrophe and recovery. We stand on Snowball Earth. Its rocks are beneath our feet. Its legacy is in our DNA. Its lessons are written in stone for anyone willing to read them. The ice came. The ice stayed. The ice melted. Life survived. Life thrived. That's the story the ancient rocks tell. What story will we write? Will we be remembered as the species that understood these lessons and acted on them? Or as the species that knew better but couldn't find the will to change course? The choice is ours. The ice was a warning. The survivors are proof of resilience. The explosion of life that followed is evidence of possibility. Snowball Earth happened, but it ended. Catastrophe struck, but recovery followed. That's the final lesson, that even the most extreme states eventually give way. That change, however dramatic, is not permanent. That the planet endures and life adapts, and ultimately the story continues. Snowball Earth is behind us. The question is what lies ahead.